Here we're going to develop the idea of spontaneity. We've talked a little bit about spontaneity before, and here we're going to put it on a more firm foundation. The two examples we used, or two of the examples we use for a spontaneous process, is suppose we have two metal blocks, and this is high temperature and low temperature. What we find is that a spontaneous process occurs. Heat flows from the high temperature to the low temperature block. This is a process that happens spontaneously. There's no urging. It just happens. A second example we used in class was a case where we had two gases, argon and helium, same pressure, same temperature, and they were separated by a partition. If we now remove this partition, what we find is that argon distributes evenly and helium distributes evenly in this volume. That happens spontaneously. It just happens. And in fact, we never see the reverse happening. We never see argon collecting over on one side and helium collecting on the other side. Just as we never see heat being transferred from the low temperature to the high temperature. It's always one way. It's spontaneous. It just happens without any urging. And the colloquial expression, shit happens. Oh, I probably shouldn't say that, so let me go out back and bleep that out. All right, so what we have from our discussion of the second law is things happen spontaneously if the entropy change in the universe during that process is greater than zero. That's the definition of a spontaneous process. You start someplace and then you end someplace else, and if the entropy of the universe in that second place, that final state you end up with, increased, then going from the initial to final state was a spontaneous process. Now let's look at this. This says that the entropy change at constant internal energy and volume is greater than zero for a spontaneous change. Let's just see that. Okay, this is for an isolated system. Let's take, for example, the isolated system of the universe. This is the universe, which is isolated. That is our assumption. Isolated means that Q is equal to zero. You cannot transfer heat. That's the definition of an isolated system. W is equal to zero. You cannot do any work on the surroundings. The surroundings can't do any work on the system. That's an isolated system. And therefore du, which is dq plus dw, is zero. Let me just make infinitesimal changes here, dq and dw. All right, and we said for an isolated system, delta S is greater than zero for this whole system in here, and it's isolated. So what this means, let's assume we have PV work only. So this is minus P dV, PV work only. So that's the only kind of work, so that's minus P dV. And U is a constant and V is a constant. So this implies for an isolated system, the change in entropy at constant U, which is zero, du is zero, and constant volume, dV is zero, no volume change here, constant volume is greater than zero. So there it is. For an isolated system, ds at constant internal energy and volume is greater than zero. All right, so you might sort of notice we've sort of subtly switched from the entropy of the universe to the entropy of the system. And so that's what we're going to do for the next few equations, is focus on the system. So this is an isolated system. The entropy change in an isolated system where you have constant U and V is greater than zero. So this is the criterion for spontaneity for an isolated system. All right. Now what we're going to do is to make some other conditions here for constant volume and entropy, constant pressure and constant entropy, and so on. But first, before we do that, let's combine the first and second laws of thermodynamics to get the combined first and second law. All right, so the first law of thermodynamics is that du is equal to dq plus dw. The second law of thermodynamics says that dq, or ds, is greater than or equal to dq over t, where the equal sign is associated with a reversible process, and the greater than sign is associated with an irreversible process. And we said in class on Friday this will associate as a real process, something that really occurs. All right, so let's multiply. Let's take this second law here, multiply both sides by t. So t ds is greater than or equal to dq, or dq is less than or equal to t ds. All right, let's take the first law and rewrite that as du minus dq plus, sorry, it should be a minus, minus dw, that's equal to 0. Now let's use this relation here, dq, and replace that with tds. So du minus tds minus dw. Now dq is less than tds, or tds is greater than dq, but this is entering as a minus sign. So you're subtracting off a bigger number. So initially it's 0. If that is equal, this would be 0. But you're subtracting off a bigger number, so that will actually be less than 0. So less than or equal to 0. This is the combined first and second laws of thermodynamics. Now let's assume that we can only do PV work. So in that case, the combined first and second laws of thermodynamics is du minus TdS minus PdV is less than or equal to 0, where the equal is for reversible processes and less than is for irreversible processes. Or we'll just write this, du minus TdS plus PdV is less than or equal to 0. Now we're going to say, all right, du at constant s, so ds is 0, and at constant v, dv is 0, is less than 0. So this, or less than or equal to 0, but let's make it a real process, so less than 0. So this is a criterion and again, this is the internal energy, the energy of the system. This is a criterion for spontaneity, for constant entropy and constant volume. So you have some process that occurs at constant entropy and volume. You just look at the change in internal energy. If it's less than 0, it's spontaneous. Okay, so that's where this comes from. Let's look at this equation. There's a constant P and S. Okay. So we'll start with the definition of enthalpy. H is defined as, we'll write it this way, as U plus PV. That's how we defined enthalpy. Okay, let's take the differential of H. dH is du plus PdV plus VdP. Let's rearrange this to say that du is dH minus PdV minus VdP. And we've shown that we can rewrite this equation here as du is less than or equal to TdS minus PdV. In other words, take this term and this term, put it over here. So that's the what du is equal to. So we can say that that is less than or equal to, for reversible processes, TdS minus PdV. solving this equation for dH is well, actually, let's take these things and put them over there. So dH minus PdV minus VdP, put that minus TdS plus PdV is less than 0. Let's get rid of the equal, so we'll look at real processes. And how convenient, the PdV cancels out. So we're left with dH minus TdS minus VdP is less than or 0 for a spontaneous process. So this is a criterion for spontaneity for constant S and P. Constant S, constant P, dH is less than 0. dH at constant S and P. Okay, so there's where that comes. dH at constant S and P is less than 0. All right, so that's kind of interesting, you know, but how do you experimentally in the laboratory hold internal energy constant, or how do you hold entropy constant, and so on? So when you go into the laboratory, it'd be nice to have things like temperature, pressure, and volume, and hold those constant, and have some function that you could calculate to see whether it'll be spontaneous. Okay, so what we're going to do is define two new energy terms, free energy terms we're called. It's A is U, internal energy, minus TS, and we'll define, that's the Helmholtz free energy. We'll define the Gibbs free energy as the enthalpy minus TdS. It's called free energy because essentially what you're doing is subtracting off this TdS term, or TS term, which is like wasted energy, energy that goes to heat and not available to do work. So this free refers to energy that's free to do work. We'll find this at constant temperature and constant pressure and temperature here. Looks like there's a slight mistake. Let me check that. At temperature and volume. That's right, that'd be volume. All right, so let's see what this definition gets us in terms of criterion for spontaneity. All right, so we're defining A. We're going to define that as, well, let me start this on a new page so we can be more precise. So A is defined as the internal energy, U minus TS. We're subtracting off this unuseful energy entropy. All right, so dA is equal to du minus TdS minus SdT. Nothing new there. Let's solve this for, say, du. du will be equal to dA plus TdS plus SdT. And we know that du is less than TdS minus PdV. And again, just remember we're only doing PV work. That also was the case here. When we went down here, only PV work. That's one of the assumptions we've made there. Okay, so let's take this term, put it over there, take that term, put it over there. So we have dA plus TdS minus SdT. Ooh, that's kind of neat. Plus SdT, blah, minus TdS plus PdV has to be less than 0. We take those things, that is 0 less than 0. And look at the TdS terms cancel out. Ooh, so we got rid of entropy. So dA plus SdT plus PdV has to be less than 0, or dA at constant temperature and volume has to be less than 0 for a spontaneous process. So if you want something that's occurring at constant temperature and volume, and you want to see whether it actually occurs, goes forward in time, calculate the Helmholtz free energy and see whether that is less than 0. If the Helmholtz free energy decreases with this process, then the process will occur spontaneously. And finally, we get to the, just touch base here, so there we go, temperature, volume. And finally, we get to this Gibbs free energy, given the symbol G, which you probably are familiar with from introductory chemistry and other courses, other science courses. So let's just see where that comes from. G, we're going to define as H minus TS. So we're going to sort of subtract off some non-useful energy. S has units of joule or of energy per Kelvin, and you multiply by Kelvin. So this is energy. TS is energy, and you're going to subtract off from the enthalpy that energy, and we'll see what happens. All right. H is U plus PV minus TS. So dG will be du plus pdV plus vdp minus tds minus sdt. And we're going to do the exact same we did for the other 3 cases. We're going to substitute in, we're going to solve this for du. Du is dg minus pdv minus vdp plus tds plus sdt. And we're saying from the combined first and second laws that is less than TDS minus a PdV. And again, only PV work. All right, so let's take this term, put it over there, take that term, put it over there. So here we have dG, that minus PdV minus VdP plus TDS, okay, plus SDT. We're taking this over minus TDS plus PdV, and that has to be less than 0. And let's see what cancels out. TDS cancels out. There goes the entropy. PdV cancels out. So there goes the volume. And so we're left with dG minus VdP plus SDT has to be less than 0. Or dG at constant P and T, pressure and temperature, has to be less than 0 for spontaneous process. So finally we get something useful for the chemist. If you have like a chemical reaction occurring at constant pressure and constant temperature, and you want to know whether the reaction will spontaneously go from the reactants to the products, you calculate the free energy change. If the free energy change drops or is negative, in other words the free energy drops, becomes low, then the then the reaction is spontaneous. So remember at the very beginning, or maybe even from introductory chemistry, if we look at, say, the free energy versus time, we have this graph, and we have here reactants. Well, let's make this the progress of the reaction. Okay, it goes like this. It's down here. It goes like this. What you want, and this says is constant pressure and temperature, so it's just sitting in the laboratory in a beaker that you maintain at constant pressure. This is spontaneous. dG is less than 0. You're decreasing the free energy. And this way is spontaneous. And right here, it's not spontaneous. It's not going that way. You already reached a minimum, so that's the equilibrium point. So in both cases, you want to decrease free energy for a spontaneous process at constant pressure and temperature. Finally, something we could use. All right, so that's it for spontaneity for now. And in the next lecture, we'll consider some other concepts. In particular, we'll get heavy into partial differentials and variables and so on. and we'll be able to derive some interesting relations between these quantities. So just to review, what do we have? We have U, H, A, and G. So those are the four thermodynamic functions. We have U, we have H, we have A, and we have G. U is the internal energy. H is the enthalpy. A is the Helmholtz free energy. And G is the Gibbs free energy. This is useful for constant temperature and pressure. This is useful for constant temperature and volume. And this is useful for constant entropy and pressure. And this is for constant entropy and volume. So really these are the two that we have easy experimental access to these constant parameters. All right, so just remember that, and I think we'll be okay to go on. Thanks for listening.